Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. How are you? I hope all of you are staying safe at home with your loved one. Let's pray so that COVID-19 will go away and we can continue to study in class normally. Welcome to the lecture note series for ESE 551 Control System. This is the first video for chapter 2. The title of chapter 2 is State Space Analysis. So today I will give you an introduction to state space representation. State space representation is a new method for most of you since you have not learned this in control system course during diploma. In the previous chapter, we have used transfer function to represent a control system mathematically. Transfer function is a ratio between system output and system input. It consists of a numerator and a denominator. It is in S domain and it is known as a conventional method. As humans start to explore space, they found that conventional method is not enough to represent their system. So they have invented state space method. State space is in time domain. Basically, it is differential equations arranged in matrix form. It consists of state equation and output equation. This is an example of state space representations of a third order system. I will explain this in detail in the next slide. In this slide, I will explain in detail on state space representation. It consists of state equation and output equation. State equation is x dot equals to ax plus bu, and output equation is y equals to cx plus du. A is the system matrix, B is the input matrix, C is the output matrix, D is feedforward matrix. U is the input variable, Y is the output variable, and X is the state variables. To understand what is a state variable, let's consider an aircon system. The input variable is the desired room temperature. The output variable is the actual room temperature. Meanwhile, state variables are other variables exist in the aircon system such as pressure of the gas, flow of the gas, and speed of the fan. These variables is important to the system but not an input or output of the system. Next, let us look at the dimensions of the matrices and variables. X dot is the first derivative of the state variables. The dimensions of X dot is n by 1, where n is the system order. If the system is a third order system, then X dot will have 3 elements, x1 dot, x2 dot, and x3 dot. A matrix is a square matrix. The dimensions is n by n. If the system is a third order system, matrix A will be a 3 by 3 matrix. X is state vector, which consists of state variables. The dimension is n by 1. For a third order system, state vector will have 3 elements, x1, x2, and x3. For a single input, single output seesaw system, input variable dimension is 1 by 1. Next, let's proceed to output equation. Similar to input variable u, output variable y dimension is 1 by 1 matrix. The dimensions of output matrix C is 1 by n and D matrix is 1 by 1. For X and U, the dimension is similar to state equation. In some case, you will find that D is 0, resulting the output equation to be Y equals to CX only. Here I have included three examples of state-space representations for different system order. The first example is second order system. The second example is state-space representations of a third order system. And the third example is the fifth order system. If you look at all of these examples, the D matrix is 0. Thus, the output matrix is equals to Cx only. And if you look at the x dot and x variables, it is written in bold font to indicate it is a vector. For example, if the system is third order, the x will be x1, x2, and x3. State space representation also can be represented using schematic diagram. So this is the schematic diagram of a state space representation. You can obtain the state equation by referring to x dot signal labeled as 1. So it is the summations of signal AX plus BU. And you can obtain the output equation from the output signal labeled as 2. So it is the summations of Cx plus Du. And if you look at the triangle block labeled as 3 in the block diagram, it is the integration block. The functions is to integrate the x dot signal to x signal, which is the state variables. Since transfer function is in Laplace domain, while state space representation is in time domain, we need Laplace transform to convert from transfer function to state space and vice versa. In this video, I have included two tables of Laplace transform. Table 1 lists the Laplace transform of common functions such as impulse, unit step, ramp, and many more. The second column of the table shows the corresponding Laplace transform of the function. And the second table is the Laplace theorem table. We will use these two tables to do the conversions from state space representation to transfer function or from transfer functions to state space. In this lecture note, I have included two examples to demonstrate on how to obtain mathematical equation for a simple RLC circuit. The first example is on how to obtain the transfer function. The RLC circuit consists of a resistor, an inductor, a capacitor, and a voltage supply. In this example, the voltage supply is chosen as the system input and the current as the system output. Using KVL, we will get equation 1. Then, using Laplace transform, equation 1 is converted into Laplace domain, as shown in equation 2. The Laplace transform of di dt, highlighted in blue, is from differentiation theorem item number 7 from table 2, while the Laplace transform of the integration term, highlighted in green, is from item number 10, which is the integration theorem. Then, rearrange the equation to obtain equation 3. To remove s from the denominator of the last term highlighted in red, multiply the top and bottom part with s. Finally, the transfer function of the system is obtained and shown in equation 4. Example 2 shows how to obtain the state space representations of the same RLC circuit. Similar to example 1, the first step is to use KVL to get the differential equation. Then, step 2 is to select the state variables. From example 1, we know that the circuit is a second order system. Thus, we have to select two state variables. In this example, I choose the first state variable to be the charge Qt and the second state variable to be the current IT. To generate the state equation, we need to find the first derivative of Qt and IT. So dq dt is equals to I, and di dt can be obtained by rearranging equation 1. Using equation 2 and equation 3, we can write the state equation. For the output equation, we have selected the IT to be the system output. Thus, yt is equals to it as shown in equation 4. Then, write equation 4 into output equation form. In state space method, there are several terms that are normally used and you have to understand. The first term is state vector. So it is a vector whose elements are the state variables. Second term is state space. It is the dimensional space whose axes are the state variables. The third term is state equation. It is a set of n simultaneous first order differential equation with n state variables. In selecting the state variables, two rules need to be considered. First one is a minimum number of states variables that is sufficient to describe the state of the system must be selected as components of state vector. Number two, the components of the state vector must be linearly independent. For exercises related to this video, you can refer to the tutorial materials to be shared in Microsoft Teams and Telegram from time to time. If you have any question, please do not hesitate to contact your lecturers. And I think with that, I will end the session. Thank you very much for your attention.